Good morning, everyone. My name is Greg Aranda with Graybar, and I'd like to welcome everyone to Graybar's G2 Talk presentation this morning called The Basics of Machine Safety. This talk is part of our webinar series that we offer each month to our industrial customers. We have a great discussion lined up for you today, but before we get started, I'd like to cover just a few housekeeping items. First of all, if you are one of the first 50 people to join on the presentation this morning, you will receive a coupon for a free cup of coffee, courtesy of Graybar, as a thank you for your time today. Also, at the bottom of your screen, you'll see a box for questions and answers. Feel free to submit questions throughout the presentation, and we'll address as many questions at the end of the presentation as time permits. Lastly, our G2 Talk webinars are all archived on graybar.com, so you'll be able to view this presentation again or recommend it to others. We're happy to team up today with Phoenix Contact. As a full-service distributor, Graybar works alongside Phoenix Contact to provide a wide variety of automation and control solutions. With safety being top-of-mind concern for every work environment, we're happy to partner with Phoenix Contact to provide products and solutions that will help you prevent accidents, protect employees, and be OSHA compliant. At this time, I'm happy to introduce today's speaker, Zachary Stank, Product Marketing Specialist for Safety Products at Phoenix Contact. Zach has a bachelor's degree in chemical engineering from Penn State University, and before joining Phoenix Contact 4 years ago, Zach worked in quality engineering for the defense sector, where he specialized in vehicle inspection and test reporting. So without further delay, I'd like to turn things over to Zach. Take it away, Zach.
Thank you very much, Greg, and welcome everybody to today's webinar. Today we'll be talking about the basics of machine safety. Again, my name is Zachary Stank. I'm a product specialist here at Phoenix Contact. And today's presentation should take about 35 minutes of total presentation time, followed by a Q&A afterwards. If you have any questions during the presentation, please submit them to the Q&A, and we'll be answering all questions at the end of the presentation. So a real quick agenda. I want to really touch the majority of this on the understanding of safety concepts. In the United States, it can be very difficult to understand if you're doing something correctly and even to know where to look if you're doing anything correctly. I will briefly talk about some practical examples in the machine building OEM sector and possibly in the process industry as well. And then in the end, we'll talk about the new CE standards that are in Europe and how they apply to us here in the United States and what exactly they mean. So before we start, the first groundwork is to understand what is safety. So if you're going to the Merriam-Webster website to look up safety, you'll get these definitions. But really, the main thing to understand safety as is the freedom from the occurrence of risk of injury, danger, or loss. What does that mean for us in the machine building world? Well, really, there are three functional areas for safety: inputs, logic, and outputs. Inputs being guards, stops, sensors, light curtains, things like that, and your outputs being contacts, drives, motor control systems, those type of operations. And in between those two is logic, so that's relays and controllers. And logic is really what interfaces the inputs to the outputs and what creates a safe circuit. So for Phoenix Contact and safety, we focus primarily on the logic section of this, so relays and controllers. There are some Phoenix Contact devices that are drives or hybrid motor starters, but we don't do any input sensors at all. So when you think of Phoenix Contact safety, we're talking just the logical portion. So I'm sure most of you have seen this before. What is a safety relay? Besides being a yellow-colored relay, a safety relay is a little different than a safety standard relay in that it carries some type of safety certification with it. Certifications are typically done for performance level, category, or SIL. They give it a special rating that it's been prepared to handle certain types of risk. And really what a safety relay does is it monitors input to make sure that your devices are working properly and that your e-stops or your input channels are not malfunctioning. And it also monitors a machine start or reset button. It also looks for welds on the output channels as well to ensure that they're working properly. And for most relays, you can also bring in your output, normally closed contacts, into your restart to ensure that any welds on the output channel will be identified. So from a more visual standpoint, you're monitoring the inputs, making sure that they work, monitoring the reset to ensure that there's not a fault on the reset, and you're also monitoring your output contacts to ensure that there's no welds. So very, very basic look at what a safety relay does. So now, understanding the basics of a safety relay and what safety is. The main reason we do safety is because it's required. And the requirements for safety in the United States are all driven by OSHA. I'm sure everybody's familiar with who OSHA is and what they are. The Occupational Safety and Health Administration. Their Subpart O 1910 of their standards of Title 29 outline the basics of machine safety that are required under the OSHA clauses. As you can see there, it's not very large. There's about 7 of them there, with the most important ones being the 1910-212, general requirements for all machines. And of course, if you're doing any woodworking, cooperage, abrasive wheel, mills, mechanical power presses, forging machines, and mechanical power transmission, you're also outlined in those standards. They're all freely available on OSHA's website. It's www.osha.gov. The Subpart O is what you're looking for again. And again, you can just go through all their standards online there. So I know most of you are thinking to yourself, great, my application isn't listed by OSHA, so I don't have to do anything. That's not entirely true. The OSHA standards are quite old. I think the most recent update to them has been in the 80s, but they're always being discussed and taken online by OSHA. The other thing that OSHA has is a right to reference clause. Essentially, OSHA is allowed to reference any nationally recognized standard and bring it into law at any time. So, for instance, they recognize NFPA 79 as the National Electric Code. So that is something that you need to follow. The other thing that OSHA can do is they can hold you to any nationally recognized standard. So if you are making a machine and you're following an ISO standard or an ANSI standard based off your machine, they're going to want to see if there's a problem with that machine, what you followed, how you followed it, and why you did what you did. So for example, there was nothing in the OSHA standard that really applied to your machine. You can go to the ANSI standard. There's tons of ANSI standards beyond what I've listed here. They've partnered with RIA, some other corporations that do some nationally recognized standards. So they drive from all facets of industry in the United States. Again, the most important ones here are B1119, that is a performance criteria for safeguarding. That's an important one to make sure you're following. If you have any specific applications that are listed here, you want to make sure that you're following them. And then another one to understand is B11TR3 there at the bottom. That's risk assessment and risk reduction, and we'll talk about that in a little bit. But again, the most important thing to realize is that just because you have what you covered doesn't mean that you looked at the standards and you're okay to go. You want to make sure that you cover all your bases. And the best way to do that is, one, to understand what it is you're working in. So if you're in robotics, you definitely want to reference the RIA standard. If you're machine building, ANSI typically covers that. Oil and gas has a couple different standards organizations. They pull from the IEC. They have a couple local organizations down there in the Gulf of Mexico that you want to follow. So it's important to go through everything and make sure that you cross your T's and dot your I's. But a lot of people don't know where to start once they actually have read and understand what they're supposed to be doing. How do I start developing safety, or where do I go to look and see if I've done safety properly? And the best answer to that is a risk assessment. Now, OSHA does require a risk assessment. However, they don't require it to a specific standard. So in here, I've listed a few standards that you could follow. Corporately, Phoenix Contact follows EN ISO 12100 for our our risk assessments. But any of these standards here will be good to go through and walk you through a proper risk assessment. So that being said, there's 4 steps to a risk assessment. There's determination of the machine limits, hazard identification, risk estimation, and risk evaluation and reduction. All these steps are very important, but I think one that a lot of people miss is the determination of machine limits. And what that is determining what are the parts of my machine, what is the most important things in my machine, what can I qualify or quantify. And a lot of people jump right to hazard identification, step 2, without actually going through and writing in everything you need to understand about your machine. And as a flow here, it's important that you start at the top so that you can follow the logical path to creating a safe system. So for example, if we had a depalletizer, palletizer, depalletizer, you would want to record the dimensions, the weight, electrical, air pressure, cycle time between a pallet, material loaded, how's it loaded, when's it loaded, the product life, how long is it designed to be used for. And while I'm saying you want to be doing this, your risk assessment team really shouldn't be a single person or just a single type of engineer. You don't want to have all mechanical engineers looking at a single machine because they'll look at it as a mechanical engineer would look at it. You want all different facets of your corporation involved on risk assessment. So you want floor operators, you want maintenance technicians, electrical engineers, you also want your machine engineers, maybe some desk office people that would look at it a different way. It's very important to include everybody in your organization in the risk assessment, not just so that you feel inclusive, but also that they bring different sets of eyes to each different type of application. So recording these down is important because now I have a list of ideas, or I have a list of what my machine actually is, and that's how I identify what my hazards are, or what my hazards are. Without this list of actual operational items from the machine, it's hard to identify hazards. Yes, you can go through and look at a machine and figure out what it's done, but if you're not actually quantifying what you're looking at, you could be looking over certain aspects of the machine. So the last 2 steps are probably the meat of everything, is risk estimation and risk evaluation and reduction. How likely is this event to happen? How dangerous is the event? How can the risk be mitigated, and is there a safety system required? One big thing I see a lot is people get into the risk assessment. They start identifying the different risks on their machine. They'll have spinning blades, moving items, issues like that, and they'll try to protect everything with very, very complex systems. Now, very complex systems do work, but they're not always required. A lot of times for a spinning blade or moving hazards or crushing hazards, a simple gate or just guarding against like a fence or something like that would be sufficient in order to do it. And a lot of people jump right to adding safety product to it. There are situations where guarding against somebody coming into the apparatus is not possible, and a safety sensor and safety logic is required. But a lot of times you can build out the inherent risk of a system just by keeping people out of the area. And really the risk evaluation reduction needs to be done if, at times to load material or anything like that, people need to be within a hazardous area, or if there's maintenance time where you need to have specific safe control of a machine. So again, everything starts at the beginning by documenting it, and then at the end, you want to make sure that not only are you documenting, but you're also trying to make sure that the documentation is easy to read and that you're not jumping to conclusions. So you want to understand the design features. Can you design out safety, or design in safety, or design out hazards to protect your workers or protect your machine from itself? If that's not possible, then again, you want to take protective measures. So try to keep people out of the area, stop motion, stop hazardous power when somebody enters that area or has to do something. And then most importantly, documentation. It's always important to label and put down hazardous areas or high voltage or things like that. So a documentation step is very necessary in doing your risk analysis. So what are some of the protective measures you can take? You could do covers, like I said, gates, guarding. Protective doors will allow you to go in when necessary while turning off something. And then you want to protect material ejection. So if you can build a gate around something that's, again, or a fence, it's an excellent protective material. You definitely want to be able to avoid people walking by and being in a hazardous area just without even interfacing with the machine. So putting in some type of gate or guarding material so that it protects the machine from ejecting is also a very good thing to follow. So after you go through your risk assessment, you may have determined that a safety function is required. Again, this is an iterative process, so you don't want to just say, yes, we need to do some type of safety. Okay, we'll put e-stops everywhere and we're done. You want to define that safety function. One, because if you over-design, you'll be spending way too much money on safety and over-designing it for your application. And then, of course, if you under-design, you could be at risk for possible hazards and loss of life or product. So it's important to understand how much safety you need. The best way to do this is really to look at the European standards at the moment. The two big European standards right now are 13849 and 62061. 13849 is commonly considered the performance level standard. So you hear performance level and category, they're all lumped into 13849. And then the IEC 62061 is the SIL standard for machine building. So that the parent document for that is 61508 and 61511. Also, that's the ANSI S84 standard. So the big thing here is to understand that in Europe, machine builders are ultimately responsible for safety. So from the time that you have the concept or you begin to think of an idea or put pen to paper for a machine, from the time that happens all the way to the end of life, 20 years after the machine is built, you're ultimately responsible for ensuring the safety of that machine. So that means while you're building it, you're making sure that no new hazards have been created, that there's no accidental use of power or somebody gets crushed while it's being done, or you don't accidentally allow power to start, and also to provide maintenance schedules and the estimated time of life cycle of this machine. So as you're going through, it's very important to understand, especially when you're shipping out to Europe, that legally you're held responsible for this. Whereas in the United States, it's not as clear cut that the builder, the operator, and the owner of the machine ultimately have some type of responsibility for it, but it's not as clear cut as in Europe. So we're going to take a look at this also because there's been a lot of adoption of the European standards globally. Japan, Australia, and some other countries have started to incorporate this 13849 standard into their own national standards. The new RIA ANSI R1506, which is now ANSI RIA ISO 10218, actually is quite the same as the 13849, and it uses some of the 13849 terms and ideas to get to where they are in their standards. So it's coming. The ANSI hasn't directly made its own standard like this that would mimic something like this, but it is in the works. So we talked again about there used to be an old standard that was, category-based. It was ISO 954. So if you're familiar with safety categories, essentially you had single channel and double channel. That has kind of been reworked and added some actual math and technical items in there to ensure that you're not just designing safety based on the needs of how much you can spend, but also the needs of the actual machine. And from a flowchart perspective, it's quite simple. You ask yourself, is the machine safe? How do you reduce risk? You can do it by construction, again, using safety equipment or user information. And if it requires a control system, that's when you need to start looking into how this needs to be done. So again, like I said previously, there's three separate parts of a safety system when it comes to machine building. There's input, logic, and output. And it's very important to analyze all three facets of this. They're all taken together. Think of it as a chain, and you're held to the weakest link of that chain. So if you're using really good sensors and logic and processing equipment, but you haven't really considered safety on your output side, the weakest link in that chain would be your output, and you'd be beholden to that the type of safety that you got from that output side. So according to the standards 13849, you really want to go through and figure out what performance level is required. You need to design it, you verify it, and then validate. So design is taken, again, from an actual statistical point of view. There's something that is called the probability of dangerous failure per hour. It's graded from A to E, so performance level A all the way to performance level E. The low end of the performance level A is low risk, so probability of dangerous failure per hour is every 1,000 hours. So if you're thinking about that, you can have a dangerous failure and every 1,000 hours of use of that machine, and it won't be that dangerous. So low risk is minor injuries, bruises, small cuts, maybe some loss of actual material. Whereas high risk could be loss of limb life and lots of material and or damages to structures. So that's at once every 10 million hours there. Very high risk, and you're essentially making it sure that dangerous failures are very, very infrequent at the high end. So this is done through a required performance level risk graph. Essentially, you start at the end here, and this is taken from 13849, the standard. The first question you ask yourself, how severe is the injury? So S1 is reversible, S2 is irreversible. So if you can think of reversible as small bruises, small cuts, when you start to get to breaks and losing pieces of flesh, then you start to get to the S2 area. So how reversible is the injury, or how severe is it? Duration, how frequently is somebody in there in the hazardous area? Anything above once per shift is considered frequent. So if you're only in the hazardous area for maintenance once a week, that's F1. But if somebody's in there constantly removing input and output material, that would be F2. And then the final thing is preventability. How easily can you prevent the risk? So if I have a slow-moving press that I can notice that it's coming down and get out of the way very quickly, that's very preventable. But if something moves very fast, or it's a robot and it's doing lots of quick movements, that's not very preventable. So you would use this graph to basically figure out which one of these performance levels do I need to meet. Once you have that, then we get into design and technical implementation. So if you're familiar with the control categories, they're still used within this. So B1 and 2 are essentially single channel design. I have a single input with a single wire going into a single logic controller that would go out to a single output. And remember, I said that the weakest link in the chain is what you're going to follow. So if I have redundant inputs going into a single logic controller, and they're like daisy chained, then the single input would be the single channel input would still be only single channel. If my outputs are going outside of my main cabinet and they're being daisy chained on the output side, then again that would be single channel there. Category 3 and 4 are redundancy. The difference between 3 and 4 is 3, not all errors are monitored, whereas 4, all errors are monitored. And that was kind of the problem with the old standard. It was tough to understand when some and all became the same. So if we look at here, we also include component quality now. So MTTFD is the mean time to failure dangerous. That's not to be confused with the MTBF. They are related, but they are not the same. So the MTBF is mean time between failures. for safety, you're not looking at the mean time between your failures. You're looking at the first time you have a dangerous failure, because that first dangerous failure is going to be the problem. So they incorporate that, something called diagnostic coverage or test quality. So from category 2 on up, you need to account for this. This is all within the standard. It tells you what percentage you get, and most force-guided contacts will give you a 99% diagnostic coverage when used properly. And the final thing is common cause failures. So measures against common cause failures. This is literally a list of things you can do defined within the standard. So protection from EMF, using tried and true components, using different wiring methods. You pick several of these, or identify a few of these that you've done, and that list gets you to 65 points, and you've achieved the measures against common cause failures. It's a very quick thing to do, but it can be confusing at first. So if we go back to the control categories, we look at it here. Here's a real quick slide that you can reference of safety categories for design. Again, the most important thing to remember is B1 and 2 are single channel, and 3 and 4 are dual channel the entire way through. So B and 1 are going to look like this: single input, single logic, single output, while 3 and 4 would be redundant input going into redundant logic. And just so you know, redundant logic could be in with a single housing, like a safety relay. You would just have 2 inputs for a single, or for a redundant logic monitoring, and then redundant outputs out to the field. And the difference between 3 and 4 is you can see there's dotted lines between the monitoring here in 3, and then solid lines within 4. So the solid lines identify that you have a really high diagnostic coverage. You're able to determine whether there's been something amiss within the rest of your setup. So again, we understand categories. It's something we've all done. Then we have component quality, test quality, and measures against common cause failure. Really what these do is they get you to this graph. This is the relationship between diagnostic coverage, category, and mean time to failure dangerous. And there's a really specific way to read this. So the first thing you want to do is identify what category you're using. So let's say, for an example, I'm using a category 1 or B design for my system. So then I would identify this here. Oops, I screwed up. Sorry about that. Try that again. So I would identify that by clicking here, or not clicking here, but seeing where my category B is at the bottom. So you can see category B, category 1, I would fall within this range. If I were anywhere else, category 2 or above, I would then take into account my diagnostic coverage. So you can see there category 2, 3, and 4 have different DC averages. The difference between category 3 and category 4, again, is that some faults are determined in category 3 and all faults are determined in category 4, or everything is monitored. That is essentially the difference between DC medium and DC high. So I've identified my area here by my category design. I'm category B or 1. Now I need to go ahead and identify what type of component I'm using. I'm using an MTTFD that falls within the medium range. These, just so you know, the low, medium, and high are actually quantified within the standard. I just didn't think it was necessary to go through those calculations here. If you actually read the standard, it'll give you what low, medium, and high mean for each of these. And most manufacturers now provide this information along with their safety sensors or their safety relays. So I can take it, look at my medium within this category here, and you can see that I fall within this range. So I have a motor protection B when I decided to use category 1 or 2 with these type of components. Again, let's say I already have an existing system, right? And I did it like this. My 2 inputs that I had here, they're performance level E type light curtains. My safety relay is a performance level E, is the highest rating it got. I don't know what my contactors are, but I went through and I did my calculation. I know that my contactors had an MTTFD of a medium, and I was only using single channel. So in that graph, I was able to figure out, oh, it's a performance level B is the best I could do there. So again, weakest link in the chain, even though the two, my inputs and my logic are performance level E rated, because of my design and my output, I'm only performance level B within my system. Now, a lot of confusion comes within that because there's some things that you can do to do redundant outputs with a single channel output. So one output going to two different contactors. That's something called the fault exclusion principle. It's talked about more in the standard, and essentially what it means is that you can use a single output from a logic device to control two contactors as long as they're within the same cabinet. And essentially what you're doing is you're protecting against a cross circuit that is more typical when they're outside of the same cabinet. So if your contactors are in the same cabinet as your logic module there, it's very frequently done with a single output going to two in-series contactors. So I know this is a bit overwhelming, especially for a 30-minute presentation. But the nice thing to know is that there is a software available, and it's not a Phoenix Contact software. It's actually a German professional institute that created it. It's called Systema. Systema takes in all the standards, the 13849 standard information, and incorporates it into a really easy-to-use software that's free. It'll walk you through the specific steps and the different parts of your system, ask you questions, what design are you using, what category, do you have diagnostic coverage? A lot of manufacturers now also include a library for Systema. So if you're using, for Phoenix Contact parts, you can incorporate the library of our parts into Systema, bring them in, and it really makes your calculations easier. The nice thing, again, is it tells you the required performance level that you need. You can determine your achieved performance level, and it gives great documentation to go along with your machine in the end. So it's a click-based system in an open window where it does all the documentation for you, and then you could print it out on the end and deliver it with your machine. And this is a free download. Again, it's the link is there. It's the BGIA. Out of Germany, and it's directly helpful with the 13849 standards. And with that, that's the end of my part of the presentation. I'll turn it back over to Greg, and we can do the question and answer.
Thanks, Zach. That was a great presentation. So yeah, just a reminder for everybody, if you have a question, please submit it in the Q&A box at the bottom of the screen. We did get a few in, so I'll go ahead and go over those with you, Zach. And since you're talking about the 13849, so does OSHA recognize that as a safety standard?
So OSHA only requires that you do a risk assessment, not that. I'm sorry, was the question about the risk assessment? Is that right, or was it about the 138?
About the European standard, the 103849.
Yeah. So sorry about that. The 13849 is not directly referenced by OSHA anywhere. The RIA doesn't have anything that is directly, it doesn't exactly match up with 13849, but some of the other standardization bodies are starting to incorporate 13849 practices in theirs. So for example, the RIA already has a standard up, the 10218. The ANSI RIA ISO standard that directly references 13849. So the answer to it would be no, OSHA doesn't directly say to use the standard or that it meets requirements, but the nationally recognized bodies that OSHA requires and that requires and makes you use are starting to use it. So by default, yes, it is being used throughout their standards, but no, it's not a requirement of OSHA.
Okay, cool. I had a question here. Can a U.S. machine manufacturer affix a CE marking on their equipment when they ship their machine to any European country?
So the answer to that is yes. CE is a self-certification. Phoenix Contact actually has an app to help you walk through the CE labeling process. It's a safety app. And it basically asks you a few questions about your machine and what you're doing. The machinery directive out of Europe is what drives the CE marking for machines, and it is basically requirements that you use 13849. But by applying a CE marking on your machine, you are inherently saying that you've followed the machine directive. So yes, you can do it, but you need to be sure that you're following all the requirements of the CE marking.
Okay. I wanted to let everyone know if you'd like to sign up for a safety assessment with Graybar and Phoenix Contact, you can type safety into the Q&A box, and we'll forward your information on to a local sales rep and get that started for you. We'll get another question here. Should a risk assessment be performed during each different stage of the machinery, such as design, installation, production, etc.?
So if you're taking safety at the highest priority, really from the beginning of just concept of the machine, you should have a risk assessment done while you're designing the machine. It's very difficult to do that. Sometimes you don't notice certain aspects of a machine until you're walking around it. But it's important to start that as soon as possible. So you may have a continuing risk assessment where you look at a machine, look at different parts of the machine that you've created, what's there, and you start to do designs on that. But sometimes when you're designing in basic control systems to mitigate risk, you can create new risk. So it's important to do different, revisit it several times. It's not to say that just doing it once isn't okay. I mean, in the standards, you can just do a risk assessment of everything, and to the best of your knowledge, I've covered everything that's in here, and then you sign off on it and continue on. But from a safety perspective, it'd probably be a good idea to do it multiple times or to revisit it and make sure that anytime you make a change to a machine that no new hazards are created.
Okay, in a previous slide, you had a list of all the risk assessments. Which ones are required by OSHA?
So let me go back to this slide here. Give me a second. So OSHA itself, and I believe this is a slide we're being referenced here. OSHA itself does not specify a specific standard to use. OSHA only requires that a risk assessment be done. They have gone on record of saying that the risk assessment does not affect the overall safety of the machine. I have a differing opinion than that. I think that a good risk assessment would mitigate a lot of risk in a machine, probably simplify design and also reduce unnecessary costs, and also protect people better than, say, somebody walking around and saying they didn't see any risk. But none of these are specifically said by OSHA, but you can follow any of these. They're national standards, and again, it's always important to have documentation around, because if there is a problem with the machine, OSHA is going to want to see all the documentation with it. And these risk assessments allow you to create documentation based on the standards. So it's not a specific one in general, but it is required.
Okay, great. I'll just remind everybody, we have a few more seconds here. If you do want to sign up for that safety assessment with Graybar, you can type safety in the Q&A box. And I think we're just about out of time. So Zach, I wanted to thank you for your time today, and wanted to let everybody know we will follow up with an email with the slide, with Zach's slides and the replay probably tomorrow. So once again, you can review our archive presentations on graybar.com. And we thank you for your time today. Thanks again, Zach, for pitching in.
Thank you, Greg.
All right. Thanks, everybody. Have a good day.